Today I'm going to discuss about the intramolecular interaction in the double helix. Okay, so starting with the double helix structure of DNA. It is stabilized by various types of intramolecular interactions. I will discuss about the key interactions that contributes to its stability. First of all, I will discuss about the hydrogen bond. The hydrogen bond is the nitrogenous bases in DNA. It's adenine, thymine, cytosine and guanine that pair specifically through hydrogen bonds. Adenines form two hydrogen bonds with thymine A and T, while cytosine forms three hydrogen bonds with guanine C and G. These hydrogen bonds help hold the two strands of the DNA helix together. Next one is the base statics interactions. The aromatic rings of nitrogen bases are stacked on top of each other, which contributes to the stability of the double helix. These base statics interactions are primarily due to van der Waals force and hydrophobic effects, while nonpolar regions minimize their exposure to water. Talking about the phosphate backbone interaction, the sugar and phosphate backbone of DNA is negatively charged due to phosphate group. The electrostatic repulsion between these negative charged groups is mitigated by the presence of cations like magnesium or sodium ions in the cellular environment, which helps stabilize the structure. Now if we discuss about the hydrophobic interactions, the interior of the double helix is largely hydrophobic due to nitrogen base, while the sugar and phosphate backbone is hydrophilic. This arrangement creates a favorable environment for the base to stack together away from the water, further stabilizing the helical structure. Ionic interactions. If we talk about the ionic interactions, in addition to cation stabilization of the phosphate back group, ion interaction can occur between charged groups in the DNA and surrounded molecules, contributing to overall stability. The intermolecular interactions work together to maintain the integrity of DNA double helix, allowing its function effectively in general information storage and now further, if we discuss about the thermodynamics of melting of the double helix. So we will discuss about the thermodynamics parameters, the enthalpy, the entropy and the factors. First of all, the melting of DNA double helix, often referred to DNA denaturation. It involves the separation of two DNA strands of the double helix into a single strand. So this process is influenced by thermodynamic principles and can be described in terms of several factors. Like, first of all, if you talk about the thermodynamics parameters, the melting temperature. It's crucial parameter that indicates the temperature at which half of the DNA are denatured single stranded and half remains in the double helix state. So if you talk about the enthalpy, the change in the enthalpy during the melting reflects the energy required to break the hydrogen bond between base pairs and disrupt base statics interactions. Generally, more stable DNA without the higher GC constant has higher enthalpy because GC pair from 3 hydrogen bonds compared to 2 for AT pair. If we talk about the entropy, the change in entropy during melting account for the increase in disorder as structured double helix transition to two separate DNA. Denaturation increase the overall entropy of the system because the two single strands are more disordered than the organized double helix. So we can say that G is equal to H minus TS. Okay. When G is negative, the process is spontaneous. At the melting temperature, G is approximately 0, indicating that the system is at equilibrium between the double standard and single standard states. So, discussing about the factors influencing melting temperature, several factors can affect. Okay, first of all, base pair composition. GC rich regions have higher melting temperature due to their greater number of hydrogen bonds and stronger base statics interactions compared to AT rich regions. Now, the melting curves. The transition from double standard to single standard DNA can be monitorizing using absorber spectroscopy. As DNA melts, the absorber at 260 nanometer increases due to hyperchromic effect, where single standard DNA absorbs more UV light than double standard DNA. This result melting curve can provide information and the stability of different DNA sequence. The thermodynamics of DNA melting is a complex interplay of enthalpic and entropic factors that dictate the stability of the double helix. Understanding these principles is crucial for various applications in molecular biology, including PCR, DNA hybridization assay, and understanding general materials behave under different conditions.